Welcome back to Math and Beats. In this video, we're going to be going over a concept called average rate of change of a function. Very important concept in mathematics. Here we go. First of all, let's just define what a rate is. By definition, a rate is a special type of ratio of the form A over B, in which A and B have different units of measure. Clearly, A and B also have some numerical value attached to them. And a rate is often expressed using the words A units per B units. You know, we could make things up like, for instance, 2 miles per hour. That is a rate. Numerator, miles, units, and denominator, hours, units. A rate. Or, you know, make up something silly like 7 speakers per square foot. Numerator, speakers units. Denominator, square feet units. So, you know, you can make up any ratio like this that you want, and when it's relevant, it can have a nice significance depending on the situation. So what we want to do is dive in to the mathematics of it and what's the conceptual meanings, these kinds of things. Oftentimes, by the way, very common known type of rate is, of course, a velocity or a speed. Here, miles per hour, that is a speed, and also a velocity. We'll talk about what's the difference of those two later, but most people understand those types of things. Commonly used in language throughout the world. It's just now we're like, well, what about the mathematics? So let's take a look. And in order to take a look at this, we're going to have to just briefly refresh our knowledge about the slope of lines. So remember, when we talk about a linear function here, f of x is mx plus b is the slope-intercept form of a line expressed as a function. That number m, that tells us the slope of the function because it's linear. And what does it tell us? Well, what's up with slope? Slope tells us how fast the line increases or decreases. Just so happens to be that linear functions have a constant slope. So, for instance, say you have 2 points that are on the graph of a line, then we can talk about the slope. So let's let those 2 points just be arbitrary. x1, y1 is the first order pair, and x2, y2 as the second order pair. You can see them here in the diagram up there where my arrow is, top right. That is the ordered pair x2 comma y2, and that point right there is the ordered pair x1, y1. So just refreshing this because this concept of slope of a line is directly related to the concept of average rate of change. And remember what it tells us, slope. Well, we just said it tells us how fast the line increases or decreases. But if you set it up this way, you just pick 2 points on the line, any 2 points, and then we talk about the ratio of the change in the y direction, the output direction, over the change in the x direction. Those changes being y2 minus y1 on top and x2 minus x1 on bottom. That's the corresponding vertical and horizontal changes on the interval of consideration. And you can imagine if x and y had some corresponding units associated with them, then this ratio would be a rate. So let's keep going. it brings us to the next topic, which we also need for average rate of change, called secant lines. So this is a line that, given any function, not just linear, just any old function now, a secant line for the function is a line which intersects at least two distinct points on the graph of the function itself. And these 2 points are usually given in a situation, or we have to figure out which 2 points we're considering. And it allows us to talk about what's called the average rate of change. So just remember this idea, secant line, a line which intersects at least two distinct points on the graph of f. So for example, here is a function y equals x squared. Let's just draw a rough sketch of it real quick, just to refresh our memory. All right, there's my beautiful axis system, and label the horizontal x and the vertical axis y, and we will try to draw a nice, we will try to draw a nice, man, what happened there? That's some crazy stuff. Sorry about that, but we're now going to try to draw the parabola. Yeah, not bad. That's just the graph of y is x squared here. All right, good enough. Now, if we go to the x location of -2, let's just say maybe about right there is -2, and you know, disregarding the scales here, the output there would be 4, and then at the x location of 3, somewhere over here, the output is 9. So we want the equation of the secant line between these two x values. Of course, now if you just connect the dots, we can draw secant line. So, you know, this right here is just some particular secant line which happens to be passing through the points -2, 4 and 3, 9 for the function y equals x squared. Question is, what's the equation of this line? And we probably should try to think about what the slope of this line is as well. Well, we're going to have to, because we got to find the equation. So to find the slope, that is, remember from above, the change in the y direction over the change in the x direction. The change in the y direction is a distance from 4 to 9. So the distance between those 2 points is going to be 5, the difference of 9 minus 4, and the corresponding distance in the x direction is the distance from -2 to 3. That's 5 units, but technically it's 3 minus 2. So we see here that the slope is going to be 5 over 5, which happens to be 1. Nice how that worked out. So what is that telling us? It tells us that for every 1 unit we move over in the x direction, we move 1 unit in the y direction vertically upward. So we know the equation of this line, let's just call it y, is going to be mx plus b, and we just found our slope. Slope was 1. What about the b? Well, let's just plug in a point into the general equation and find out what b is. How about if we use the point -2, 3, which we know is on this line? So using -2, 3, we plug in the corresponding x and y and get that 3, which is y, is equal to the slope, which is 1, times the x value, which is -2 plus b, and solving that equation gives us that b must be 5. Hence, this secant line is just x plus 5 here. So that's great, but hopefully it gives you a decent idea what's up with these secant lines. You could do this for any function for whatever 2 points that you want, as long as the function is defined. All right, enough of this secant line. We'll see it again, but first we want to talk about what really is average rate of change here, because we've been talking about all these lines and slopes and stuff. Here's how we define average rate of change in general. It is just the net change in the output direction over the net change in the input direction. And if the function happens to be called y equals f of x, which it is in this diagram, then the corresponding output change on the interval here, a to b, arbitrary values of x, the output change will be that change right there, the difference in the outputs of f of b and f of a, respectively. The corresponding input change in the x direction, is the difference of b minus a. And so we see that if we take the ratio of these, we're going to get what's called the average rate of change of the function over the interval a to b. That tells us how much has the function's output changed over the corresponding input change on this interval. Well, gee, that sounds a lot like what we just did in the last problem for that y equals x squared. And indeed, it's exactly that. If we draw a line through these 2 points here, as so, well, by definition, that's a secant line. What's the slope of the secant line? Slope of secant line is f of b minus f of a, change in the output direction, over b minus a. And so what we see is that really the average rate of change of a function is just the slope of the corresponding secant line passing through the 2 points of consideration. That slope tells us, so whatever this number is some number, right? It tells us, on average, how much the function f has changed vertically per unit of horizontal change. The rate of change of the function on average. Slope of a secant line. All right. Now, there is notation that we're going to use. We're going to look at some examples here in a moment. But, you know, people use different notations. Once you study some calculus, which I'm not assuming anyone knows in this video, you will learn there's other notations as well. But I'm not going to do any calculus notation right now. I'm going to use the notation that I like to use, and that is, instead of writing out the words average rate of change every single time we want to find one of these things, I just acronym it and called it AROC. AROC. Over what interval? Well, because the average rate of change in general is going to be different depending on which interval you're looking at. So I like to say it's the average rate of change of the function, say f, as a little subscript, over the interval a to b. What is it? It's f of b minus f of a, change in the output direction, over b minus a, the change in the input direction. So we'll use that in the upcoming examples. Hopefully, so far, it's pretty clear. Okay, moving down here. Let's look. Here is our first example we're going to look at. We're going to consider the function g of x's square root of the quantity x minus 1, and we would like to find the average rate of change of this function over the interval 5 to 10. Okay, so what do we find? First of all, the notation, the average rate of change of the function g over the interval 5 to 10 is going to be, just like we saw above, g of 10 minus g of 5, the change in the output direction, over the change in the input direction, 10 minus 5, which is just plug it in. First one, square root 10 minus 1 minus the quantity, plug it in, square root 5 minus 1 all over 5, and that is square root 9 minus square root 4 all over 5. Square root 9 is 3 minus square root 4 is 2 over 5, 1 over 5. So what's that tell us? On the interval 5 to 10, this function g of x, which is square root x minus 1, changes on average 1 unit, what am I writing? 1 unit vertically for every 5 units horizontally. Or equivalently, you could say that for every 1 unit horizontally, it moves up 1/5 of a unit vertically on average over this interval. And just to get a better idea, make sure we understand graphically what's happening, we draw a rough sketch of this situation here. So the graph of the square root of x minus 1 looks something like that. There's our graph, square root x minus 1. And then you go to the points, 5 to 10. Maybe there's 5 and there's 10. Boom, boom. Draw a line through them like so. The slope of that secant line is 1/5. And it tells us, just as consistent with the sketchy graph we just drew, you move over 5 units in the horizontal direction, you're only going up 1 unit in the vertical direction. So it's telling us on average it's getting bigger, right? But kind of slowly. All right, so there's one example. How about another example? And now for the next example, let's consider the function m of t, which is negative quantity t minus 3 squared plus 9. Let's let that be the function which gives the amount of money a person has in their bank account in hundreds of dollars t days after the beginning of the month April, where we're counting it for the first 8 days. What we want to do is figure out the average rate of change of the function m over the interval 2 to 5, and then talk about what it means within the context. So we want to find the average rate of change of the function m over the interval 2 to 5. What's that going to be? Change in the m direction, so m of 5 minus m of 2 over the change in the input direction, 5 minus 2, and then we're going to go ahead and evaluate it. So m of 5 is quantity negative 5 minus 3 squared plus 9 minus the quantity m of 2, which is negative quantity 2 minus 3 squared plus 9 all over 3. And then that first part, 5 minus 3 is 2. 2 squared is 4, so that's a negative 4 plus 9. And then minus the quantity, 2 minus 3 is negative 1. Squared is 1, so it's a minus 1 plus 9 all over 3, which is 5 minus 8 over 3, or negative 3 over 3. Of course, that simplifies to negative 1. The units here, which have on the numerator, the units are in hundreds of dollars. And then the denominator there has units of days. So, what's this really tell us? On average, this person lost $100 per day in their bank account for the days of, well, if t equals 0 corresponds to the first day of April, then t equals 2 corresponds to the third day of April, And t equals 5 corresponds to the 6th day. So for the days of April 3rd to April 6th. So they might have been spending more money than they were bringing in, or they didn't get paid or something, and on average, they were spending $100 a day out of that bank account. Maybe one day they spent $300. Maybe one day they spent $0. But on average, they were spending $100 a day from that bank account. So you can see, it can help us kind of talk about things in the real world too. We have one more example here, and it has to do with velocity, which is a very common application of this. Let's suppose that a ball is thrown upwards into the air off the top of a roof house. The ball's position S in feet, t seconds after it's been hit, or thrown, should I say, can be modeled by the function s of t here. What we want to do is find the average velocity of the ball between t equals 1 and t equals 3 seconds. So first of all, I just want to make sure you understand what this word velocity is. This is just speed with direction. So whether you're going upwards or downwards or to the left or to the right or eventually any direction, the direction matters. And that's what we want to find, the average velocity over this time interval. So what are we going to do? Average rate of change of this function s over the interval 1 to 3 is given by s of 3 minus s of 1, changing the output direction, over 3 minus 1. And now we got to plug it in. So s of 3 is negative 16 times 3 squared plus 32 times 3 plus 48. And then minus the quantity, negative 16 times 1 squared plus 32 times 1. And then plus a 48. All over 2. All right. So we got to multiply this out. You might want to trust me because I got the calculator here handy with me. The 3 squared is clearly 9. 9 times a negative 16 is negative 144. So that's negative 144. And then plus 32 times 3 is 96 plus a 48. All of that minus the quantity, negative 16 plus 32 plus 48. And then we take all that divided by 2. In the first parenthesis, negative 144 plus a 96 plus a 48. This actually is 0. And then minus the quantity, negative 16 plus 32 plus 48, 64. All over 2, that gives us negative 32. And then what's the units here? Well, the outputs are in feet, so it's negative 32 feet. And the inputs are in seconds, so negative 32 feet per second. What's it tell us? On average, the ball travels downwards of a rate, and here that's the velocity, the speed with direction, of 32 feet per second on average. So there you go. You've been introduced to the concept of average rate of change, and we saw a few examples. I hope that it helps you and you're able to do problems on your own a little better now. And even if you don't like all this math, at least I hope you like the beats, because guess what? It is time for Bees Lights.